In this project, we set out to predict temperature as well as explore classification based on weather summaries. To do so, we imported a suite of essential libraries and models. We began by loading tools like Pandas, NumPy, and Matplotlib for data manipulation and visualization, along with Seaborn to create insightful correlation heat maps. For our machine learning models, we brought in several regression and classification algorithms from skip-learn. This included linear regression and ridge regression to establish the baseline, and classifiers such as k-nearest neighbors and logistic regression for our categorical task. Importantly, we also introduced the random forest regressor. This ensemble method builds multiple decision trees and averages their predictions, which greatly improves their stability and accuracy in prediction. Here, we will load the dataset using and reading the data frame using pandas. Here are the respective information. So now we focus our understanding on the data by generating a correlation matrix. The heat map revealed, among many features, that there were two key variables that had very high correlation with our target variable, the temperature. The insight was critical because high correlation features tend to drive the performance of tree-based methods like our custom-made random forest model. In addition, we undertook meticulous pre-processing. We filtered out unneeded columns, such as, for example, here, we filtered out loud covers. Then we handled missing data using forward filling. And most importantly, we transformed categorical data into numeric values. For example, we define functions to convert various weather summaries and precipitation types into numeric codes. This allowed all features to be used effectively. We trained several AI ML models by extracting the features and targets of the dataset. Now, on the regression side, our linear and ridge regression models both performed impressively, achieving R-squared scores of around 0.990 on both training and testing sets. The error metrics such as MSE and RMSE were very low, indicating that these linear models captured the underlying trends quite well. For our classification, we experimented with k-nearest neighbors and logistic regression. Although these models yielded accuracies in the 24%, their performance was notably less robust compared to regression models when it came to predicting temperature. Now, finally, onto my custom-made model that was taken. It is the random forest regressor with an MSE close to 0.003, an RMSE of just 0.055, and a perfect R-squared score of 1 on both training and testing sets. The random forest model demonstrated its capacity to handle complex nonlinear relationships within the weather dataset. But here's the evaluation of the performance of the models. As you can see, here's the graph for linear, ridge, and random forest. Now, this is plotting against the predictor to the actual temperatures that have been measured. As you can see, relative to the best fit line, the random forest has the least amount of variance relative to the best fit line. Now, onto our fine-tuning process, we begin with the ridge regression, where we varied the alpha parameter while tracking the RMSE and R-squared. Although its performance was similar to the standard linear regression, the L2 penalty reduced overfitting and managed to multicollinearity by shrinking large coefficients. Next, we tune to the k-nearest neighbors by incrementing k up from 5 roughly to the size of the square root of the training set size. We found that k equals 8 improved the test accuracy the highest from 24% to 25%. As you can see by this graph over here, it peaks around k equals 8. Now, for logistic regression, we adjusted it by switching from L1 to L2 regularization, increasing the maximum iterations to 1000. This change ensured all features contributed, boosting accuracy from 24 to 30%. Our original linear regression model performed remarkably well, while achieving an R-squared score of 0.990 with just 12 non-zero coefficients. With fine-tuning, particularly through ridge regression with normalization, we saw marginal improvements on the training set, reinforcing the value of regularization. In contrast, our classification approach for both KNN and logistic regression lags significantly behind, with accuracies hovering around 24%, even with fine-tuning to a maximum of 30%, which clearly illustrates for this weather dataset, regression is inherently more effective than classification in capturing the underlying trends. However, the standout result comes from our custom random forest regressor, where this model delivered with almost a perfect fit, with a test MSE of 0.03 and an RMSE of 0.05, and a perfect R-squared score on both training and test sets. Not only does this confirm that regression is the superior approach here, but it also shows that random forest regressor is the best overall model, outperforming even our fine-tuned linear methods. Thank you for your attention.